Right, this is the problem that we are trying to solve. It's a free boundary value problem, which means you impose boundary conditions, but the surface on which you impose them is free to move in response to the solution. These are all the equations. We've got equation for the first order metric perturbation, equation for the second order metric perturbation, and we're working, say, outside of the buffer region, so out this region out here. This middle curve is gamma, the world line of the center of mass, and then this region around the world line is the buffer region. So say we're in the buffer region or beyond. So out there, we are solving these vacuum equations for H1 and H2. And then we have a free boundary condition, which is that the solution has to look like what we derived from matched asymptotic expansions. So it has to look like the self field that we derived, where we have an analytical local form for it, plus some regular field that's a smooth vacuum solution at the world line. That's the form you have to recover in the buffer region. But the location of this buffer region is moving in response to your solution because the center of mass world line is accelerated, and the acceleration involves the regular field that you're getting. And the buffer region is always around that world line, so this whole boundary in the buffer region is free to move in response to your solution. Then we also want to impose boundary conditions at the future horizon of the big black hole and at Scri+. So we want outgoing waves out at Scri+. Waves are leaving, nothing is coming in, so you don't have anything coming in. And similarly, you don't have anything coming out of the white hole. You just have gravitational waves falling into the horizon and coming out at Scri+. You also have this constraint equation. So this is all using the Lorentz gauge setup in the self-consistent framework. Now, as I said before, if you satisfy this constraint equation on some initial hypersurface, then these equations are constraint preserving. So you'll still automatically satisfy that to the future of this hypersurface. Okay, but what I'm describing here isn't what will ultimately be used, because what's ultimately used is the 2-time scale expansion, where you start with these equations, do a 2-time scale expansion of these equations, and then solve those. But I'm just going to stick with this for simplicity. Okay, so here I want to enforce that the local solution in the buffer region looks like what comes out of matched asymptotic expansions. But I'm now going to do the same thing I described at the end of the last lecture and just analytically extend this local solution all the way down to the world line. And then a completely equivalent problem is if rather than just solving outside the buffer region, you solve these equations at all points that are not on the world line. Where now you analytically extend these down to all points that are not on the world line. So the solution to that problem is going to be exactly the same as the solution to the original problem, except in this very tiny region, which looks big on this picture, but that's exaggerated. It's an incredibly tiny region. You don't really care about what's happening inside that region. You only care about what's happening outside. Okay. Now, how does the puncture actually get involved? So we've done this analytical extension. And now I'm going to replace this as, rather than having to agree with this form in the buffer region, you can just say near the world line, at points near the world line. Okay, so we've done this analytical extension. Now, why is this called a puncture scheme? So we take the local analytical form we have for h bar s, and we truncate it at whatever highest order we've got. So some finite order in R, where R is distance from the world line. So as I said, we have this for n equals 1 up to order R out of the 4, and we have it for n equals 2 up to linear in R, including the linear in R term. Then call this truncated expansion, this is our puncture. Now let's define a residual field h bar curly r, which is, let me call this h bar p. So h bar p is equal to h bar s up to order r squared differences, say. Now we're to define the residual field to be the full field minus the puncture. Then if h bar p is h bar s, say plus order r squared differences near the world line, then h bar curly r is equal to h bar non-curly r plus order r squared. Because if we put this expression in for the puncture, we get the full field minus the singular field plus order r squared, and that's exactly the regular field plus order r squared. So what this means is we can replace HR with H residual in the equation of motion 3. So this residual field determines how the world line is accelerating. Now let's make this residual field our numerical variable. So we solve for the residual field rather than the full field. What that means is, if we go back to our equations over here, H1 is HP1 plus H residual 1, and I'm just going to move the HP1 over to the right-hand side. And similarly down here, I'm going to move the HP2 over to the right-hand side and just have the residual field on the left. So then we have E alpha beta of H bar residual 1 equal to minus E alpha beta H bar P1. So the curvature of this puncture, the curvature of this singular puncture in space-time, is acting as a source for the residual field. And then similarly at second order, and again this is for all points that are not on the world line. So at second order, we have second order residual field is equal to 2 delta squared G alpha beta H1. This is the full H1, not HP1 or H residual 1. And then minus E alpha beta H bar P2. So remember I said earlier on that this is extremely singular. like m squared over r to the 4 at the world line. This is exactly as singular. So the singularities cancel, and you get a nice smooth source for your nice smooth residual field. Again, this is for all points not on the world line. So we can write this more generally as E alpha beta H bar residual n, the nth order, is equal to an effective source, S effective, which is just the source when you've got the puncture on the right-hand side. So there's a little bit of mathematical subtlety here. Because I also said that the full physical field, H1, you can express exactly as if it were sourced by a delta function, point particle stress energy tensor. So then you'd think once you move this over to the right-hand side, you should have a delta function minus this, rather than just minus this. So the key thing here is I'm treating these as ordinary functions at all points away from the world line. Arbitrarily close, but away from the world line. And this is not treated as some distribution, it's treated just as an ordinary function at these points. And then if you want to move it on to include the world line, then you define it on the world line just by continuity, by taking the limit from off the world line. Now, it's slightly different than if you were treating this as a distribution, in which case this operator acting on HP1 would actually introduce a delta function if you're treating this as a distributional quantity, and that delta function would cancel the delta function you would have added on the right-hand side. The net effect is identical either way. You're always left with just an ordinary function that, if HP1 is sufficiently high order, is just continuous at the world line, and differentiable any finite number of times you want if you make your puncture high enough order. So yeah, so here I'm ignoring things like the delta function. I'm taking the limit from off of the world line after evaluating this operation acting on HP1. And so now we have differential equations that are defined globally, not excluding the world line. Okay, so this is the scheme that is used in second order calculations, because, as I said, you can't actually get the retarded field by solving an equation with this as the source, because the source is too singular. So you kind of have to use this puncture scheme. At first order, this is also being used using a puncture scheme, but then you also have the possibility of just directly calculating the full H1 and then afterwards subtracting the singular piece to extract the regular piece that goes into the force. So that's an option at first order, not at second order. But basically, this is the picture in general, and it's easy to extend this to arbitrary order, where now you have a puncture that's singular on this world line. So the world line essentially just is where you have this puncture in space-time. And then you're solving for the residual field that goes into the equation of motion, which tells you how that puncture then moves through the space-time. Now, a technical point is that the puncture was defined as an expansion in powers of r. So say you go up to r squared, then that's actually getting bigger and bigger and bigger as you go far away from the world line. So you actually don't want to use this everywhere. What you can do is just say this is radial distance, and you've got your singularity there. What you can do is say your puncture is singular here, And if you go far enough away, as I said, it starts increasing, but you can just put an envelope on it so it goes down to 0. And again, that's not changing what the residual field is here, so it's not changing the acceleration. And it just means that far away, the residual field, outside some distance here, is just equal to the full field. So it transitions from being the regular field at the particle, or at the world line, to being the physical field at some distance away. Or you can do just a sharp transition, where you just jump from here down to there. Those things will give you identical results for the motion and identical results for the physical field h. Okay, but now what if you did want to calculate the retarded field, the physical field h, and then subtract the singular field afterwards? How would you do that? So as I said, you can't do that at second order, at least using current formulations, but you can at first order, and the method you use to do that is called mode sum regularization. So here we can solve for the full field H1 using the point particle equation. Solve for the retarded field H bar 1. Over here you have a point particle source. Now, how are we going to subtract the singular field from that to extract the regular field that determines the self-force and therefore the motion? It's very, very hard to do that if you just have the four-dimensional retarded field, which blows up at the world line, and then you try to subtract the singular field to get something finite. That's difficult to do because as you get closer and closer to the world line, both of those objects get more and more large, numerically large. So you're trying to subtract one big number from another big number to get a small number. And that's numerically very difficult to do. So instead of working with the full field, we work with individual modes of the field. So modes here means spherical harmonic modes. And these are spherical harmonic modes around the big black hole, not around the little black hole. So we can imagine, let's say we want to calculate just the regular field on the world line. Then this is the limit from off the world line of the full physical field minus the self field, singular field, or puncture. They'll all give you the same answer here. But now let's expand these in modes. So expand both of the fields in modes. And then we have the subtraction mode by mode. And this is just the first order field, first order field, first order field. This won't work for the second order field. Alpha beta, T, R, YLM, theta, phi. Now let's take this limit in the radial direction. So it's independent of which direction you take it in. So let's just pick the radial direction, which means we're now taking r goes to, say, rp, the position of the particle. I'm going to write this as just a sum over L of h L alpha beta r minus h s L alpha beta r, where these individual L modes is just having summed over m, from minus L to plus L. So here we have HLM, alpha beta, and I'm evaluating at the time on the world line that I'm going to, R, and then YLM, and the theta position and the phi position of the particle. So I'm just approaching in the radial direction. Okay, now the magic is that we can now take this limit inside of the sum. So the sum there is equal to sum over L of HL alpha beta, evaluated now at Rp, minus HSL alpha beta of Rp. The reason you can take the limit inside the sum is that this sum is actually uniformly convergent. So you can, use the Weierstrass M test or something like that to prove uniform convergence, and then once you know it does uniformly converge, you can bring the limit inside. So now we have just a mode of the full field at the particle minus a mode of the singular field at the particle, and at first order, both of these are perfectly finite at the particle, and so the difference between them is perfectly finite. Then you add up the modes, and you end up back with the regular field that you wanted at the particle. Now in practice, we find that HSL alpha beta Rp in the Lorentz gauge is just equal to a number. Well, a number depends on Rp, with no L dependence. It's independent of L. So then what we've got is that HR on the world line is just a sum over L of H L alpha beta Rp minus this number B. And this gets called regularization parameter. So mode sum regularization is by far the most commonly used method of calculating the regular field in self-force calculations. You'll get a slightly more complicated formula for the self-force, but same basic idea. And you can analytically calculate what these regularization parameters are. So then the big picture is you solve the linearized Einstein equation with the point particle source over here. So you solve this subject to the boundary conditions you want, which is outgoing waves at infinity, waves going down the horizon at the big black hole. You solve it numerically. In the Lorentz gauge, people have done that, or you can solve it numerically in different gauges, the Reggie-Wheeler gauge, the radiation gauge. Anything other than Lorentz gauge tends to introduce pathological singularities, but we know how to work with those pathological singularities to get the physical quantities out. But the idea there is then you're going to work with the mode decomposition anyway when you're solving this, especially in Schwarzschild, where everything's spherically symmetric. You're going to expand H1 in spherical harmonics, or more likely tensor spherical harmonics. You're going to expand T in spherical harmonics. So the numerical output of your calculation is going to be this mode you want anyway. So you have what you need. You calculate this in advance for a generic orbit, and then you just subtract it off, add up the modes, and you get your answer. So this, in practice, is a lot easier to implement than a puncture scheme, which is why it's much more popular. Now, the reason it doesn't work at second order is that the individual modes here actually diverge on the world line, logarithmically with distance from the world line. Okay, so this is to calculate just the regular field. Now, what about calculating the force? So say we want the first order force. So we're going to do the same thing. So the force is automatically a quantity on the world line. We're going to write it. We're going to take the radial limit. In this case, you need to decide whether you're coming from larger r or smaller r, because individual quantities will depend on which direction you approach from, but the combination of the quantities is independent, so it ultimately doesn't matter. You just need to be consistent, term by term, whether you're coming from outside or inside. Then we're going to have sum over L. And now we're going to have individual L modes of the force. What that means is it's the force constructed from individual L modes of H1 minus the same thing, but now constructed from individual L modes of the singular field. So in the Lorentz gauge again, this has a very simple form. F alpha L1 constructed from S1L is L plus a half times A alpha. And this does depend which direction you approach from, whether you're approaching from greater R or smaller r. But this depends in the exact same way on which direction you approach from, so the end result is independent of that. Plus B. This is a different B. Not the same B as over there. So the only L dependence is this L dependence here. These are both independent of L. So again, you calculate the modes of your first order field. You calculate the modes of this force from that. You calculate this analytically, which allows you to calculate this. These both need indices. Calculate these parameters analytically in advance for a generic orbit. And then once you have the modes of your field, I should do the one more operation of bringing this limit inside. Then you have everything you need to calculate the self-force. Okay, now I just want to quickly run through an example of why the individual modes are finite in these cases. So it may not be obvious why each mode over there is finite, or especially why each mode over here is finite. Metric perturbation in flat spacetime. So we want a first order calculation in flat space So since the world line is approximately a geodesic, if you're in flat space, that means it's approximately just a straight line. So we can approximate this as a straight line. And then the singular field has a very simple closed form. If we choose an inertial frame that's co-moving with this straight line, then we have first order singular field is 4m over s. So here I'm using s as the distance from the particle. So to not confuse it with the r, let's say this is your origin over here, and r is the distance from the origin. So in flat space, this is exact, you have no corrections. And the TI component is just identically 0. And the space component is also identically 0. The only non-zero component is just the TT component, and it's just a Newtonian gravitational potential, 4m over the distance from the particle. Now, HR, alpha beta, is a smooth solution to the Lorentz gauge field equation with 0 on the right-hand side. But in flat space, the Lorentz gauge field equation is just the flat space wave equation. It actually doesn't matter whether you have h bar here or just h, it's still true. All right, so let's say you have some solution to this. It could be an incoming wave that just passes through the particle. I guess that's all it can be. Now, let's see what happens with the mode sum regularization. So this is in coordinates t, xi that are co-moving with the particle, and xi equals 0 at the particle. Now let's switch to another coordinate system with the origin over here. And now the particle is at a position xi in this new coordinate system. And it's going to be at a constant position. So we're still co-moving, but we've just translated a little bit away. Then, in this new coordinate system, let me put a prime on there to make it clear that it's not the same coordinate system I was writing that over in. And over here, this s squared was just x squared plus y squared plus z squared. Now we're in a primed coordinate system. So in t xi prime, the world line is z alpha, let me put a 0 because I'm using the geodesic approximation. World line is t xi prime 0, which is some spatial position. Now let's calculate the regularization parameters. So let's take what we've got over there and write it as the sum over modes. Now, hopefully you've seen this formula for just 1 over distance from a point in terms of spherical harmonics. So we can write this S as square root of delta ij x I minus x naught I times x j minus x naught j. Square root around that entire thing. So how many of you have seen the formula for just 1 over distance from a point written in terms of spherical harmonic sum like this? Or you might have seen it in terms of a Legendre polynomial rather than a spherical harmonic. So most of you, okay, good. So yeah, that's a standard formula for inverse distance from a point. Now here, r less than and r greater than are referring to whichever is greater between r and r naught, or whichever is lesser between r and r naught. So r less than is the minimum of r0, and r greater than is the maximum of r0. So this means that, say, you're outside the radius of the particle here, you're out here, then r less than is just the radius of the particle, and you're dividing by the radius of the field point you're evaluating at. And that means that this number, r less than over r greater than, is smaller than 1, which means that as L goes up, this factor gets arbitrarily small, gets exponentially small. But now, if you actually go to the world line where r is equal to r naught, then that factor, you don't have any suppression with L. On the world line, this will become just 1 over r naught. So it doesn't get smaller with L. So say we wanted to calculate the B parameter, this B parameter here. So this was just evaluating the individual modes summed over M, evaluated at R naught or RP, in this case, same thing. So that was the sum over M minus L to plus L. And here we've got 16 pi M over 2L plus 1. And now at R equals R naught, again, this factor just becomes 1 over R naught. And we've got while M star of theta naught phi naught times while M of theta phi. But this is defined This L mode here is defined where you're evaluating on the particle. So now the sum over m here can actually be written as a sum over Legendre polynomials. This is just PL times cos of the angle, let me call it angle alpha. This is the angle between the point in the first argument of the y star and the point in the second argument. But in this case, they're the same. So this is actually just PL of 1. And that is just 4m over r naught, if I'm not mistaken. So it doesn't depend on L. So this is what we call B in this case. I've dropped my indices. This is HSTT. And yeah, over here this should be TT. All the other components are just 0. Right, so this is the very simplest case. You just got a static particle or a particle moving at a constant speed in flat space-time. And the regularization parameter is just 4m over r0. Assuming I've done this calculation right. It wasn't actually written down in my paper. But it's something like that. Now, this is the kind of thing that goes into the final exercise, making use of this specific example of a particle in flat space, and what happens if HR1, or if you're imposing static boundary conditions on HR1, what happens? Is there a force or not? Or if you impose that this is just a wave coming in from infinity, then what happens? Is there a force or not? Okay, so this concludes the discussion of practical calculations, and this is the last thing I wanted to say. All right, any questions? Yeah. Yes. So this is this B. So you get a different set of regularization parameters for every quantity you want to construct from the regular field. So this is the B associated with just the field itself. For the force, you'll have a different B. And yeah, this should have had a couple indices over here. And this should be BTT. And all the other B's are 0. So one of the interesting things about mode-sum regularization is that when you're looking at more and more singular quantities, if they're just constructed by linear operations on HS, or linear operations on the retarded field, the modes don't actually ever get more singular. They're always the same. You just get higher and higher powers of L. So the force is a derivative of the field. The field diverges like 1 over distance. So the force diverges like 1 over distance squared, but in a very particular way, where when you do the mode decomposition, that 1 over distance squared just goes you from having no L up to L plus a half. And if you look at a quantity constructed from 2 derivatives of the metric, you just get L squared here, and so forth. So powers of R, or powers of distance from the particle, just become higher powers of L. But that's because of the particular structure of a linear operator acting on an integrable function. That is not the behavior that happens at second order, where you have products of singular functions, and the higher degree of singularity does not translate into a higher power of L. It translates into something that's still singular at the world line, even after doing a mode decomposition. Any other questions? All right. Okay.
So that was the last lecture of this school. So on behalf of ICTS, the organizers, and all of you, Let me thank Adam for giving this wonderful course. This really important area of theoretical gravity, which would have a lot of practical applications when the LISA flies in the next 20 years.
Yeah, so what I didn't describe is what is the actual status of real calculations? How far along in the project are we? So this is a program of research that started in 1996 when Misatakawa derived the first order equation of motion. So that's 23 years ago now. And in that time, we've gone from not being able to calculate the first order force at all to being able to calculate the first order force for generic orbits in Kerr. So that took 21 years to get from the formula for the self-force to actual concrete calculations of the first order self-force in Kerr for generic inclined eccentric orbits. Now, what we want is, so let's say we draw a table here. We have Schwarzschild, and we have Kerr, and we've got first order, and we've got second order. So ultimately, what we want is to be down here. We want second order calculations in Kerr. So getting first order calculations in Schwarzschild, this happened in 2008 for generic orbits in Schwarzschild. In Kerr, we now have generic calculations at first order as of 2017. Now I derived the second order equation of motion and the local puncture in 2012, 7 years ago now. And we are now just barely getting results for quasi-circular orbits in Schwarzschild. So again, 20 years to get first order in Kerr. We had 20 years from the time I derived the second order puncture and second order self-force, 20 years from then until when LISA flies. Same amount of time it took to get the first order results. But so far, we've used up 7 years just to get not even a complete calculation, most of a calculation for quasi-circular orbits in Schwarzschild at second order. Now we're down to about 15 years to go from this to go to this. And one important thing to stress is that, okay, we are now in principle capable of doing calculations at first order in Kerr. But we only have one guy who's done that, and he's only run his code, 5 times, except for testing, many, many times. And we have a huge parameter space, a massive parameter space. We have 2 masses. People are just now starting to add spin to the small object, so that adds more parameters. We have the spin of the big object. We have eccentricity. We have radius of the orbit. We have inclination of the orbit. So we have a lot of parameters, and we need to populate that entire parameter space in some clever way. Right now, we've got 3 points, maybe 5 points in that parameter space filled, excluding the Schwarzschild case where we have it completely filled. So there's a huge amount of work that needs to be done before LISA flies. I'm in charge of one work package in the LISA consortium. So in the LISA consortium, there are these work packages that are determined by what's called the LISA Science Group to be things that need to be done before LISA flies in order to be able to achieve the science goals that we say we're going to achieve in our research grant proposals. And in the proposal that went to ESA to get LISA funded. We said we're going to do certain things. We need to do all the work in these work packages to actually be able to do those things before LISA flies. So there's two important things in here. One is work package 1.2.1, and that is develop Emery models. And that's the one I'm in charge of. Then there's another one, 1.2.2, which is implement the models and actually calculate waveforms. And Niels Warburton is leading that. There's a lot of gray area in between the two work packages. So often, development of numerical methods is part of Emery model development and vice versa. But we talk to each other every week anyway, so it's not a big problem to have a bit of overlap. So there's a huge amount of work that needs to be done. We need to populate the parameter space with first order self-force data. We need to get things working at second order. And right now, the method we're using to calculate second order quantities in Schwarzschild is just not going to carry over directly to calculations in Kerr, so we need actually development of methods. And then once we've got that, we then need to populate the parameter space with second order data. It's going to be completely impossible to actually just do millions and millions and millions of second order self-force calculations numerically, because they're going to be way, way, way too slow for that. So we need clever ways of deciding, okay, what points do we actually need in the parameter space? And ideally we'd have some kind of surrogate model that would simplify our lives, and we just need as few points as possible of actual numerical data to calibrate that surrogate model. So there's a lot of work that needs to be done on that side. And then, of course, there's also a lot of work that needs to be done actually doing the second order calculations. A huge amount of work still remaining there. So we actually are very keen to have as many young people as possible moving into the field and doing the really important, crucial work that needs to be done. Because as I said in the very first lecture, if you don't have the second order contribution to the phase, then this 20 years of work at first order was essentially out the window, and it doesn't help us. So if you're at all interested in this, I highly encourage you to join the field. We are desperate for young people. There's about 50 people who show up every year to the annual meeting, but I'd say 15 of them actually consistently do work in this field. So it's a pretty small community, and we need young people bringing new ideas and new energy to get this work done. All right, is that a good enough pitch? Next CAPRA meeting, so the annual meeting I mentioned is called the CAPRA meeting. CAPRA is the film director from the first half of the 20th century. It's called the CAPRA meeting because the very first one was held in a ranch that Frank Capra, the director, owned and had donated to Caltech. And then the name stuck. The next one is going to be in Austin, Texas. It's usually in June or July. So it's going to be very, very hot, but you're used to that here, so it's okay. It tends to have back and forth between America one year, outside of America another year. But now most of the community is actually no longer in America, so it's less frequently in America now. The last one was in Rio last month. Yeah. So as I said, we have some results for circular orbits, and it's almost a trivial step to get the waveforms out of that. For orbits in Kerr, we're not nearly as far along as we should have been, because it's adiabatic approximation, including an efficient way of calculating the Carter constant, so not just using flux balance arguments. that adiabatic, a very practical, fast adiabatic method was developed 2005 to 2007. And in principle, as soon as you had that adiabatic method done, you should have been able to just start pumping out waveforms. But what actually happened was people said, okay, this is going to work, and then they never did it. They just, I guess they thought LISA is a far way off. We don't actually need waveforms right now. But now, Niels is really pushing to actually start generating these adiabatic waveforms. So the waveforms that are used in data analysis right now, so right now there's something called the LISA Data Challenge, which is a group of data analyst people who are developing data analysis techniques for LISA. And part of that includes data analysis techniques for Emory data. The waveform model that goes into there is what's called a kludge model, which means it's totally made up. It doesn't come from any physics. Well, it comes from some physics, but not from the real physics. And it's just designed to have all the parameters that the real system has and roughly the same kind of dependence on those parameters. It's not actually supposed to be accurate in any way, or at least not, certainly not to be accurate enough to use in real data analysis, but it's supposed to be accurate enough to develop data analysis tools to analyze data. So that's what's going into the actual data analysis work right now. But Niels is really pushing to really get true adiabatic waveforms that come strictly from the adiabatic approximation and give you the leading order piece of the phase. He's mostly doing that with Scott Hughes from MIT, but there's a few people working towards doing that, because that's low-hanging fruit. We've got the methods, there's no reason why nobody's implemented it yet. But again, part of the hard work is then deciding, okay, how do I fill the parameter space? Because in this 2-time scale expansion, you're essentially moving through parameter space. So you need to populate some parameter space with data points and then evolve through that parameter space using the 2-time scale method. And you need a way of parameter. And I think that's still not known how to do well in Kerr. In Schwarzschild, people have made some progress in doing it efficiently. Any other questions or comments? Okay, thank you again.